Hello, welcome to our lesson on moment distribution method as a method of structural analysis. My name is Engineer Dr. Gideon E. Ambrose from the Department of Civil Engineering, Akwa Ibom State University. So these are the subtopics that we'll be considering in this our lesson. But just be sure that to make it simple and not lengthy, the lesson is going to be in different parts. So the method of moment distribution is a method of analyzing statically indeterminate structure. This is because the fundamental principles and equation of statics that are used to analyze structures are only adequate to analyze statically determinate structures. But many structures in practice are usually statically indeterminate. And so it is important that we learn the method of analyzing statically indeterminate structure. Such method of analyzing statically indeterminate structure include the slope deflection method, the three-moment theorem, and the moment distribution method. Now, why the slope deflection method and the three-moment theorem? They usually require developing or generating a set of simultaneous equations and finding solution to this simultaneous equation. Of course, you know that if the unknown in the simultaneous equation are much, like when they are more than 3, finding solution to such simultaneous equation become tedious. And the way that is where the method of moment distribution is advantageous because it does not involve solving simultaneous equation. It is actually a manual method. It was developed by Professor Hardy Cross in 1930, and that is what we are going to look at in this our lesson. Now, in the method of moment distribution, what happens is that the structure is initially assumed to be rigidly fixed at every joint or support, and then the fixed end moment is calculated for each span. So when we calculate them, now subsequently one joint at a time is then released. When the moment is released at the joint moment becomes unbalanced. And so the equilibrium as such a joint is maintained by distributing the unbalanced moment. The joint is then temporarily fixed again until all other joints have been released and restrained in the new position. Now, this procedure of fixing the moment and releasing them is repeated several times until the desired accuracy is obtained. Now, the experience of designers shows that about 5 cycles of moment distribution usually lead to satisfactory results. And so let's look at some basic definitions in moment distribution method. The first thing we are going to look at is the stiffness and stiffness factor. Rotational stiffness can be defined as the moment required to cause a unit end rotation without translation of either ends of the member. It is a function of the member's flexural rigidity, that is EI and L, where E is elastic modulus, I is a moment of inertia, and L is the length of the section. Now when we talk about stiffness factor, which is usually represented as with the symbol K, it is a moment that must be applied at one end of a constant section member to produce a unit rotation of that end when the other end is fixed. Now for members span hinge at the near end and fixed at the far end. Such a case, the stiffness factor K is equal to 4EI all over L. It is also the moment required to rotate the near end of a prismatic member through a unit angle without translation. That is the far end being hinged, that is for member span hinge at both near and far end. For such case, K is taken as 3EI over L. If it is confusing, I will advise you just be a little patient. Once we start looking at examples, you are bound to understand it more. We also hear about another factor, carryover factor. Now, this is the ratio of induced moment to the applied moment. The carryover factor is always half for members of constant moment of inertia, that is E. We call such member a prismatic section. Now, if the N is inch or pin connected, the carryover factor is 0. So when you for inch and pin connected support, you don't carry over moment to such a support. Now, carryover factor value differ for non-prismatic member, that is beam with varying moment of inertia. Their carryover factor is not half, and so is different for both ends. For such case, you will see how we calculate it when we get to example. We also have something we call distribution factor. Distribution factor usually acts when 2 or more members meet at the joint. Now consider a frame with this member. We have member OA, member OB, member OC, member OD. They are all meeting at this point O. Now let M be the moment applied at the joint O in clockwise direction. So you see this moment applied here in clockwise direction. Now let the joint rotate through an angle theta. So if that joint rotate through angle theta, now all the 4 members meeting, that is member OA, member OB, OC, OD, will also rotate by angle theta. Now what will happen is let KAO, KAOB, KOC, and KOD be the stiffness value of the members, the respective 4 members we have been talking about. Then you can now say that the distribution factor of member OA, that is this member OA, will now be the stiffness of member OA divided by sum of the stiffness of all the 4 members. That is what is called distribution factor for member OA. In the same way, distribution factor for member OB is the stiffness of member OB divided by the sum of the stiffness of all the 4 members meeting at that joint. So in the same manner, we can find the distribution factor for member OC and member OD in that same way. Now another thing we need to consider is fixed end moment. Fixed end moment are moment at the end of a member whose joints are completely fixed. They can be caused by external load, support settlement, temperature change, or a combination of these factors. When more than one form of load is on a span, the load are analyzed separately and then added together to find the fixed end moment. And in this our course, our sign convention will be as follows. Clockwise moment will be considered positive, while anti-clockwise moment will be considered negative. So now these are the fixed end moment of some common load cases. If you have, this is a case of a uniformly distributed load of magnitude W per length. So the fixed end moment at the left support A, will be minus WL squared over 12, while for the right support it will be WL squared over 12. This is a case of a uniformly varying motion load. The fixed end moment at the left support, that is where the moment is start at 0, is minus WL squared over 8, while for the right support here is WL squared over 20. Now take note for this case, the minus here is usually for the left support and the plus is for the right support, while WL squared over 30 is for the side with minimum load and WL squared over 20 is for the side of maximum load. So if the load was to be was to be laterally inverted, that is, we now have this side to be here. What you will have here will be minus WL squared over 20, and what you have here will be WA squared over 30. This is a case of a point load acting at the midspan such that this L over 2, this side is L over 2. For such case, the left support fixed moment will be minus BL over 8, while the right one will be BL over 8. This is a case of a point load who is not at the midspan, such that you have span the length here A and this other side is B. For such case, here will be minus BAB squared over L squared, while the right one will be BA squared B over L squared. So take note of that. Okay, we are going to look at example 1. In example 1, we are going to find the stiffness factor, the distribution factor, and the fixed end moment of the beam. So this is the beam. It has 3 spans. So the beam has span AB, span BC, and span CD. In span AB, we have a uniformly varying load. In span BC, we have 2 sets of load. A uniformly distributed load of magnitude 25 kN per meter and a point load, concentrated load of magnitude 110 kN acting at mid-span such that we have 3 meter here, 3 meter here. We also have a concentrated load here of 60 kN acting at the mid-span. You also need to take note of the moment of inertia. For this span, moment of inertia is 3I. For span BC, moment of inertia is 2I. For span CD, moment of inertia is I. So let's go ahead and define these factors for this moment. So let's start with the stiffness factor. We are going to calculate stiffness factor for each of the span. For span AB, you can see this is span AB. It is fixed here at this support. This other support, although it is not fixed, but it is continuous. And you know, when you have a continuous support like this, there is a support moment. So this span is now considered as fixed at both ends. And for such case, the stiffness is usually 4EI all over L. That's why we have 4EI all over L. The 3 here is because in this span, moment of inertia is 3I. So we now have 4 times 3EI all over L. So if we calculate that with the length, we now have 1.71 EI. That is the stiffness of span AB. For span BC here, you have moment of inertia is 2I. It is continuous at this place, so it is considered to be fixed at both ends. And for that, we are going to use 4EI over L. That's why we have 4. The 2 here is because this moment of inertia I is 2I. So that's why we have 4 times 2EI all over L. And if you calculate that, the stiffness for that span is 1.33 EI. That is what we have. For span CD, it is continuous at the support, with simply support here. It is not continuous here. So it is considered that it is fixed at one end and simply supported at the other end. For such case, the stiffness is 3 EI all over L. And because I here is just I, that's why we are not multiplying here by any extra number. So we have 3 EI over L. If you put L as 4, which is this length 4, so the stiffness is 0.75 EI. Now after calculating the stiffness factor for each of the 3 spans, we can now go ahead and calculate the distribution factor. The distribution factor is usually calculated per joint. So let's leave this one first. Look at this one. We want to calculate distribution factor for B going to A. That means we are standing at joint B. So this is B going to A. This is B going to C. So if we calculate distribution factor of B going to A, it's going to be stiffness factor of span AB, which is stiffness factor of span AB, divided by the total of the stiffness factor of the both members meeting at joint B. For this case, it is member AB and member BC meeting at B. So that's why you have stiffness factor of member AB divided by stiffness factor of AB plus stiffness factor of BC. So right there we pick the parameters that we calculated here and put them in that formula. The distribution factor at B going to A is now 0.56. Now we look at B going to C, that is the distribution factor of BC. At that time, it's just going to be the stiffness of BC divided by the sum of the stiffness of AB and BC. That's what we have here. Stiffness factor of BC all over stiffness factor of AB and BC. So we put the values here and it gives us 0.44. Now what tells you that is right is that if you add 0.56 and 0.44, it will give you 1. So the stiffness factor of all the member meeting in a joint usually equals to 1. So we now go to joint C. So we calculate the stiffness factor of CB and stiffness factor CD. So for CB, we say that distribution factor, not stiffness factor. Distribution factor of CB is now the stiffness of BC all over the stiffness of BC plus CD. That is BC CD. That gives us this over this and is 0.64. In the same manner for C going to D, we say distribution factor of CD is equal to the stiffness factor of CD all over stiffness factor of BC plus stiffness factor of CD. By the time you put all the parameters here, it gives you 0.36. Now at D, you only have one member meeting at joint D, and that is why we say that the distribution factor at D going to C is 1 because it's only member at that joint. The same thing happens at joint A. There's only one member meeting at joint A. So the distribution factor of A going to B is also taken as 1. So the next thing is for us to calculate the fixed end moment. Fixed end moment. So we are going to do it member by member. For member AB, it has a uniformly varying load of magnitude 40 kilonewton per meter at the high end and then 0 at the other end. For such that for fixed end moment for AB, that is A, at this point A going to B, the fixed end moment, remember this is a left support, so it will carry minus. And this is where the moment is high, so it will WL squared over 20. So that's why we have minus WL squared over 20, and W is 40, L is 7. So by the time we work that out, it is minus 98 kilonewton meter. At the other end of span AB is fixed end moment of BA. So fixed moment of B going to A, because that is the right support. If there is no minus, so it's positive. But because that is where we have zero load, it is WL squared over 30. So when we put the parameters, we now have this. We go ahead to member fixed end moment for DC. So that is here. We are now looking for fixed end moment at this point. So for DC, is that the D going to C because the right support, it is a positive, but this is a point load acting at midspan, so it's PL over 8 and P is 60, L is 4. So you work it out, you have 30 kilonewton meter. For CD, that is C going to D, the left hand sub of that span CD. Because it is left support, it is minus. So this This is a point load acting at midspan, so we have PL over 8, and that equals to 60, which is PL is 4 over 8. That's minus 30 kilonewton meter. So we kept span BC to be calculated live, because you notice span BC is handling two sets of load, a UDL with magnitude 20 kilonewton per meter and a point load at midspan with magnitude 110 kilonewton. So like we said, in such case, you add the fixed end moments of the two sets of load. So at B, you're going to see that is at the left support in span B. You have this minus is because it is left support. WL squared over 12 is for the UDL. And there's another minus because it is left support. PL over 8 is for the point load. So when you work out the two, this WL squared over 12, this PL over 8, it gives you minus 157.5. For the right support in the span BC, you do a similar thing, WL squared over 12 plus. It is plus because it is right support. So plus PL over 8, and this equals to 25 times 6 squared over 12 plus 110 times 6 all over 8. And that gives you 157.5 kilonewton meter. So that is it. We have been able to calculate the stiffness factor, the distribution factor, and the fixed end moment for this beam given. And this is where we stop in this example. So this is where we are going to pause or end for part 1. Be sure to watch part 2 of it to see other examples where we actually do the moment distribution. Thank you for watching to this end. Please don't forget to subscribe to this page. Thank you.